want to do something a little crazy. I want to try to derive both space-time general relativity and the standard model gauge symmetries from null geodesics and helix structure. So what is a null geodesic or a null vector first? It's essentially something that's going at light speed here. Okay, and so basically, if you're right on the light cone, then you can multiply two vectors together and see what they're parallel or not. Essentially, see if they're equal to zero, then it's going at light speed. It's like a photon, or it's like a graviton, or something like that. So it's going at light speed, speed of light, c. Now, if you're past the speed of light here, that's impossible. So you're not in a causal universe. You're like out of the universe. It's impossible to be. This is the realm of impossibility right here. And if you're within the light code, then you're just a massive particle. So something that has mass, it's slower than light. Okay. So the idea is that we have this intersection between three directions. And we can call this a local Rindler horizon. So that would be essentially a causal intersection between all possible light counts. Like in any possible directions, you have light rays, right? And they're all going to essentially intersect at a point. Okay, and that point can be like a small radius or a large radius. Essentially, this extends out to the ultimate um, cosmic cosmological horizon. Cosmological cosmological horizon. Okay, but this is a local one, so it's like there are light rays that travel around in a little circle right here, and you just need a really, really small radius, or you can make it a really, really big radius, just like the cosmological horizon. But you're going to sum them all up, and you get this local Rindler horizon. So you can build space-time based off of just kind of summing up the integral of all of these um, little intersections. Okay, and these are causal intersections, causal, so that everybody can see them within the entire cosmological horizon. Okay, it's just the intersection of everybody's point of view. Right? And that builds space-time if you do that. Right? So you build this thing called null geodesics, and you set ds squared equal to 0. And so from there, you can kind of pull out, if you want a curved space-time, you add a little metric here. You add dk, these are two different vectors. And it's kind of like dx squared, dy squared, dz squared, so you can pull these out. Um, and of course, now we want to consider this, if we make areas out of this, then what happens is we can set the temperature around the zone to be, this kappa divided by 2 pi, that's the unraw temperature. We can set the Clausius relation, dq equals T delta ds. We can go into the entropy and say ds equals dA over 4g. This is essentially, this is for like local entropy for the area, okay? Um, And if we do that, then essentially we can start to take the variation of the Q, and with thermodynamics, we can start to pull out general relativity from there. That kind of makes sense. You just got some space-time. So far we just built space, with its regular old rules of space-time and curvature and nonsense. So there's K is actually equal to dx divided by d lambda. Um, we're thinking about the flux is in like the heat load dq. This is kind of what's going on as things are sort of going through this, little vibrations are going through this. How do the vibrations like affect this environment? And this is how the vibrations affect the environment, is that you get this kind of stuff happen. Tiny little vibrations cause these equations to work. Okay, so we've just kind of built space-time there. And now we can technically, if we wanted to, we could factor this out from the null field, and we can, the one null vector, this is a vector squared, right? This is just one of them, is equal to a combination of two spinors. And you have a spinor on the left and a spinor on the left, but right, they both have a half spin. This builds a vector field. Now you can cut both spinors out and you'll be left with the Higgs scalar field. You can keep one of the spinors, either the left or the right, and you'll have the spinor field. Or you could double one of the vectors, or one of the spinors, and you get the boson field. So essentially, you can build all the fields, the quantum fields, from these spinors or from null vectors, which is interesting. Um, but what we really want to be doing is we take the plane wave that we have within our Lorentz spacetime. So these kind of build Lorentz fields over here. These are Lorentz fields. So you kind of have spacetime fields, these space-time vector fields, and you can build them into the spinor field, the fermion field, or the boson field in terms of like these are the rules of spin. So you kind of separate these into the rules of spin, and now you kind of have these different plane waves that you can work with. So you can choose that, okay, well, I want to work with the spinor plane wave, or the boson plane wave, or the Higgs plane wave. So you kind of work with that. And then you have to apply phase shifts. So you start to phase shift the plane wave. And the question is, what gauge groups do we start using to consider uh, what phase shifts we need? Like, how do we know what phase shifts we need? Well, we're going to look at helixes now. So we can look at a single helix. We can use a double helix, which is something like this. Or we can use a triple helix, which is something a little bit harder to make. But 1, 2, and here's like a third one. It's kind of hard to make these. Okay, whatever. So you have like a triple helix like this, a double helix, and a triple helix. These things are, you can basically divide a circle by 2 pi, divided by 1, 2 pi divided by 2, 2 pi divided by 3, and these gives you sort of like the waveness, or the phaseness, like the phase shift. If you went around an entire helix, or if you went around half helix, or if you did this type of triple helix type of thing. It's got 1, 2, and there's another one like this. So this single helix, double helix, triple helix. And now you want to know what is the steps that they work together. Like, how do they step together? So you're going to need to figure out what the least common denominator is between 1, 2, and 3. So you need a multiple of 1, 2, and 3. And the least common denominator is 1 over 6. So you take 1 over 6 times 2 pi, you get pi over 3. So that's interesting. So this tells us sort of like the quantum of like a phase. In this case, that's actually going to be equal to the amount of charge or hypercharge, really. It's like hypercharge quanta. These phases are hypercharges. And this is getting a little bit crazy because we're kind of deriving the entire standard model here from just the geometric structure of helixes. So all we need to do is we take our pi over 3 that we have, and we're going to multiply it by 6 over here. This is because we had to take 2 pi divided by pi over 6 makes 6. Okay, and so here we have 3. You can take 3 times pi over 3 and recover the pi. You could take 2 times pi over 3 and recover your 2/3. So we're just figuring out that, yeah, 6 is definitely the least common multiple here, and we can get that back to the 2 pi, and 2 pi over 3 section, which means that we can take our 3 gauge groups. Look at that. They just take, it's like it's like the identity matrix. And then this is kind of like a level 2 identity matrix. And this is like a level 3 identity matrix. And so you kind of have the U1, SU2, SU3, and you had to divide them by Z6, or the complex unit circle divided by 6. That's what we got here. Okay, and this is the structure of the gauge groups of the standard model. Right, so we're sort of building some very powerful ideas here. Now we ask ourselves, okay, what are the generators of U1, SU2, SU3? They just fall out naturally because you take you're sort of counting different perspectives that you can rewrite this. So this isn't anything weird. You're just taking n squared minus 1, so you're going to get 1 B boson, and you get 2 squared minus 1 is 3 W bosons, 3 squared minus 1 is 8 gluons for each group. All right, and so then we ask ourselves, well, why helixes? Why are helixes so important? Helixes, because if we take a straight line here and we let the vacuum start to twist a little bit and get a little bit of potential, like the Higgs field would, and break symmetry, all of a sudden we kind of have the weakest null geodesic excitation sort of out there, and that's the vacuum expectancy value. So we get these little twisted, slightly twisted, uh, it's just slightly twisted, slightly loopy, um, vectors, okay, the null vectors. They're not exactly perfectly straight. And the gravitational waves, you might expect, wait, well, I thought that as soon as you wiggle the null vectors, that's a gravitational wave. No, 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 no. The gravitational wave is the collection, a huge oscillation. So there's different types of oscillations. So the really small one, the weakest one is the Higgs. If it's a really, really big one that oscillates everything, you can see, like the big old slinky, well, that's a gravitational wave. Okay, now these fermionic excitations, we'll come back to that in just a second, but this is how essentially, if fermions, little defects here, these little fermionic defects, a little defect can slide along these little, it can excite this little thing and sort of wiggle down, um, or twist along essentially, sort of twist over these phases, and as it twists through the helix, then it gains phases. It gains phases, and essentially, this is relative to, the fermionic twist gives it the mass energy. So depending on how hard it twists over here, we get the left, the right, and this is the Yukawa action right here. Do you see how the Berry phase and the Yukawa are exactly the same? So you're just taking the left and the right, and you're twisting it around the center loop, and that's exactly what the Yukawa does. So we get this fermionic twist that goes, and it gives it mass energy because you're sort of expending energy to do this little exchange. Now, we need to take a look at the triangle anomalies because, well, the problem is that once you kind of have your gauge groups, you can go ahead and assign hypercharges to everything. So you're just going to assign some hypercharges. The equation is Q, is the electric charge, equals the third generator of the Pauli matrix divided by 2 in case of these things, negative 1/2, 0, or 1/2. Plus the y over 2. This is the hypercharge, is y. So for each one of the possible combinations that we can use of U, SU2, and SU3, we could start with, yeah, it's actually supposed to be switched. The SU3 should be on this side. So that way we get the coordinates correct. 3, 2, 1 is the order. A little bit better. Okay, so that way we have our 3. 3 here is essentially the color triplet, and then we have 2, which is the doublet for SU2. It's like the spin doublet. All right, this is kind of like color. This is the weak spin, and then this is the hypercharge. All right, anyway, so hyper. And so if we wanted to solve for some of these, like let's try one for example. This is a 1, 1, y. It's the easiest one. So we'll take a singlet, which has no color. We have a singlet here as well, which has no, which has a spin um, uh, of I we need to use the SU2 isospin because it's a singlet. This it's a 0. This would be the 0. This would be the negative 1/2. Sorry, this is SU2. Good lord. And since this is SU2, SU2 could be 0, 1, or 2. And based off of that, we decide whether it is one of those. I can't remember exactly how this works, but it doesn't really matter too much. So let's just focus on calculating Q equals 0 because it has a singlet. This is just a singlet here, 1. If we have y over 2 over here, then that means Q equals y over 2. And that means that if we take the electron, it's negative 1 with Q, and we can solve for y, using y equal to negative 2. right? So we solve for the hypercharge of the electron on the right side. We could do that for everything else. We could solve for the up lepton, the down, or sorry, the up quark that's left, the down quark that's left. And if you do that, you get 1/3 for the hypercharges. You do that for the up right, the down right, and for the other ones. So you get these different hypercharges if you solve for that. And there's a lot more than just these, but these are the ones that survive the anomaly cancellations. So let's figure out what the anomaly cancellations are, because you can figure out what the hypercharges for any hypothetical particle. The only ones that match the standard model are the ones that fit the Fermion diagrams, or the triangle anomalies. So basically, hey, what's up, Anish? Right now, we are taking a look at the standard model. We're looking at the standard model derived from null helixes. And what's crazy is that null helixes can derive both the standard model and spacetime. So null helixes are really crazy. Um, okay, so let's figure out what these triangle anomalies are. So these triangle anomalies are essentially you have to take a pair of bosons, so like U1, U1, SU, SU2, SU3, SU3, or the graviton, graviton, and you figure out what a loose braid is. You need to have, like, the U1s are loose braids. You can always close something with the U1, because the U1 is, like, the smallest link. And you can see how, like, these excitations get stronger and stronger. So, like, the U1 is a very light excitation, low excitation. Okay, so it's a loose braid, so you can kind of keep, you can always add on one extra little excitation, but these need to close in the sense that when you combine these things, when the sum of all these charges equals zero. And so now we consider the charges of all the fermions, the hypercharges of the fermions, and we got to cube them because we have three hypercharges. Notice how we have a helix right here. And the triangle anomalies, yeah, we have the fermion right in the middle, and we have three bosons that are attached, uh, depending on what groups we use. So, you know, we got a U1 boson here, another one there, another one there. They're all three attached to the fermion, all right? And if we look at the charges that this creates, well, let's take one example. So the electron, that's the right electron. Basically, we take the color, which is 1, times the weak spin, which is 1, times the hypercharge to the third power. And we get a contribution of -8 to the anomaly. Now we have to do that with all the fermions and add them all up and get them equal to 0. To do that, then you start to cancel out some of the random extra charges that I get, like these weird hypercharges we were calculating earlier. There's like lots of them. There's infinite, essentially. There's infinite combos over here. But the only ones that survive are these very specific ones because, well, this is one reason, is because we had to cancel out the three U1s. And the second one is this one, where we take 2 weaks and a photon. And so now we basically have to use this equation, and we're going to sum up the SU2 doublets. Like, for example, this one's a really easy one to do. You could take the quarks and the leptons that both have SU2 doublets. If we look down here, the only ones that have SU2 doublets are this one, and this one, but this one isn't going to work if you start doing the math. For some reason, you jump through it because, you know, kind of already know the answer. So the idea is that here the quarks and the leptons, these ones have 3 colors times the y. These one has 1 color times the y. So then you're going to go 3 times the hypercharge. The hypercharge is only a third down here. And then over here, the -1 is the hypercharge for these leptons. So you can see where we get a third and -1 from. We just multiply them by the number of colors. If we add these two plus 1, -1, then we get 0. So those are the only ones that actually work to cancel this particular anomaly. Once we get into the third one over here, we have the gluons with the photon. We need the SU2 triplets. These are the ones that survive. And when we do the graviton one as well, we kind of do the same thing with all the fermion count, but instead of doing it to the third power, we just do to the first power, and you kind of have to cancel out all the charges again. So when you do all four of these anomaly cancellations, you start to just cut out some of the infinite combos from here, and only ones that survive are the ones from the standard model. But you can see how the reason why we have these uh, triangle anomalies is because, well, we're making these braids of helixes. We're making helix structures, and well, these helixes are also helixes. So like these, all this stuff is helixes combined together. Okay, because why? Because well, it's sort of the maximum number of microstates that you can get with wave structures. Okay, you can't really go past 3 because then you start getting 2 and 2. So 3 is maximum. That's a combination of like 2 and 1 and stuff like that. So I don't know. The idea is that we're sort of minimizing the number of things because as soon as you take a redundant count, it's the same thing. So it's all about the minimum possible microstates of the helix structures. I think we've explained pretty much everything that we have here. You can see how this sort of helix structure explains why we have the Veneziano amplitude and the hadron scattering, because we need helixes. We need these strands to be like stuck together, and then like they'll like break apart and like split and like come into other like these triangle anomalies. Like you could flip between one or the other. So you know you're gonna need some snapping and action to be able to do that. And well, that's what string theory is trying to like explain. But we don't need infinite dimensions here. We just needed our three. We needed the Fourier space. But yeah, it's pretty cool. We could basically just get back to regular kinematics like this. So the helix kinematic is essentially xt is r cosine WT, y r sine WT. And if we just take the helix radius to 0, then you just got a line, just regular old kinematics. Um, zt equals v in the z direction times time. So this is just regular old kinematics, like x equals vt. So yeah, it's kind of cool. As you can see, we just take our plane wave, apply some phase shifts, and all of a sudden we have quantum gravity essentially. You know, we can describe both the quantum side of things and the gravitational side of things in one framework. It's the null helix structure. Null helix structure. All right, so I think that was pretty much everything. This is some pretty crazy stuff that I've been looking at for the past couple of days, but it kind of reduces things that usually are really complicated, like, you know, gravity and thermodynamics and stuff, kinematics, phase shifts. Kind of reduces them to, well, the standard model is really complicated, but it helps to sort of visualize what the standard model is doing and why the equations of the standard model even exist. They're just trying to cancel the helix anomalies. All right, you guys, thank you so much for watching. That was pretty crazy. Y'all have an